Hi, my name is Jochen Koenig. I run the American operations of Dr. Schenk. We make vision equipment for various industries, including thin film PV module manufacturing. We've been in the business for about 25 years, starting with inspecting photographic film, and now our product portfolio includes anything from non-wovens used in hygienic products all the way to wafer inspection and flat panel display components. I'm talking to you today particularly about the photovoltaic effort of Schenk. We've been with the thin film photovoltaic industry since its inception or its production launches in the early 2000s, with now probably about 80% of the thin film inspection systems come from Dr. Schenk, of all the serious efforts of mass scale thin film module production. All in all, we have about 12,000 systems with a total of somewhere in the excess of 50,000 cameras in the market. So one can say we have been catering various up-and-coming industries for many years and understand the needs of new manufacturing challenges and rapid startup times. While we have concentrated onto the front end of the process, meaning bare glass inspection, the coating inspection, the scribing process in the early years of the production, now the need also arises to take inspection into the back end of the process, meaning the EVA foil application, edge taping, lamination, and the final module check, even into accelerated aging testing, a currently very hot topic, as panel manufacturers need to prove that they have good evidence that they will be able to live up to the promises of panel lifetime over the 10, 15, 20, 30 years that these panels will need to withstand any kind of environments, from deserts to northern Minnesotan snowstorms. So with that, we are going into the back-end processing, and I will start with the inspection of edge deletion. Edge deletion, as we all know, happens after the scribing process and all the coating processes have been applied in order to provide a surface for the sealant tape to ultimately provide a seal that will keep moisture and all kind of ingress out of the panels for many, many years to come. In that, it is very important that two parts happen. First of all, that all the layers are completely removed, so there is no residue, no little layer residues left. On the other hand, there is also the subject of potentially having steps in the, for example, in the mechanical grinding, so actually too deep of a grinding over time can cause problems. The next piece of equipment for the back end that I would like to talk to you about is a tool that we have recently developed as our customers have requested such a capability inline, which means the capability to measure IV curves on the individual cell level, even in subsections of a cell, in order to map panel efficiency over the entire panel and identify critical areas. We have developed, with a roughly 18-month development cycle, a tool that will allow to do this in near takt time, meaning almost at the line speed. We will be able to fully cover a panel, about every second panel in a production line, or with a quick scan test where you probe about 50% of the panel, we could actually do every panel, and thus providing not just the per panel distribution, but also distribution trends over the lifetime of a coater between ventings and things like that. This is technology that currently is mostly available after the panel has been manufactured, only for the entire panel and not space resolved in various areas. It allows us also, by the use of LED technology, to switch between different wavelengths, particularly important for double and triple junction panels where the different layers are actually designed for different wavelength absorption. As we developed this tool, we actually came to the realization that this tool is not just an IV curve tracing and measurement tool, but because of the drivers that we had to design to current drive the panels, we actually ended up also building essentially a shunt busting circuitry. So it became a tool that actually has dual purpose. One is IV curve trace mapping down to very small areas of the panel, and the other tool is actually an active repair capability by the means of shunt busting. The next process step I want to talk to you about is the application of bus bars and collection grids in thin film panels. Of course, an important process in the step of actually collecting current throughout the panel. And also, as it turns out, as we've been applying our technology to existing manufacturing plants, also quite a common source of premature panel failure issues. May it be the bus bar kind of folding over to the application, small cracks in the bus bar, misalignment, taping the bus bar over an isolation scribe, for example. So it is vitally important that such bus bar applications, may they be paste-based or tape-based, are monitored by a vision system. It's not a very elaborate and complicated system, but a very good due diligence process prior to lamination, as it is relatively easy to fix such problems before you actually laminate the panel. Another component that goes into the final module is the back glass. Or that is the front glass, depending on the actual thin film technology. This is a component that in some of the technologies is even the sky exposed portion of the panel, meaning that it needs to require rigid standards for building codes, etc. So edge cracks naturally are a big problem for panels, as under thermal stress they can actually create a full panel crack. Then of course there are glass defects themselves that basically degrade the performance of the panel itself, and also can be sources of premature cracking due to permanent thermal stress. A very special glass is glass that has front surface texturing in order to diffuse light to enhance panel performance. We've been able to develop not only systems that can detect, even in this pattern, small defects by ignoring the pattern, but also to essentially quantify the pattern as a measure of how close the pattern is to its nominal, and then detect pattern defects such as shiny areas that are not diffused, where the pattern didn't roll into the glass, etc. So all in all, back glass also with cutouts and so forth. Of course, the drill-through holes for the conductor is an important factor, that there's no cracks or anything that could cause a problem. At the end of the process stand the actual various steps of lamination, such as the application of the edge tape, the EVA sheet itself, and the actual laminator. Prior to the laminator, it is important that the edge tape, for example, is crease-free and gap-free applied. That can be done prior to lamination. It doesn't need to be checked at the end, as then the damage has been done and the panel has been rendered useless. Same as for the EVA sheet. As the EVA sheet comes in, if it's not been qualified and certified by the manufacturer of the EVA sheet, there's an opportunity here to apply an inspection system to simply look at defects in the EVA sheet itself. Once going through the laminator, of course, one of the most critical parts are bubbles and small pass-throughs in the edge tape, a clear indicator that that panel will not last very long out there in the field and will ultimately allow water ingress and premature failure of the panel. That leads us right into the final panel. Of course, after lamination, we can look at the final panel with all the leads applied and make a quick check of the front surface as well, in order to assure that during the process no scratches or larger cosmetic defects have been introduced to the panel. With that, I conclude my little introduction of the Schenk products in the photovoltaic production lines. Particularly here, the focus on the back end, and leaves me to say that Dr. Schenk will continue to cooperate with the thin film panel module manufacturers to further increase their profitability by both providing process improvements through continuous measurement data and quality improvement through a rigorous testing protocol. I thank you for your attention, and for more information please refer to our website at schenkvision.com.